Okay, so like I said, we're going to start by deriving the shape functions again for beam element. Again, this is something that if you were actually going to write a program, you just look them up in a textbook or use ones you'd already derived. You don't have to redo it every time. But just for demonstration purposes, I'll go ahead and do it again. So we're going to start with an interpolation that looks like this. Okay. Our A matrix is X evaluated at the X location of the first element, so that's 0. And then minus the derivative of X with respect to little x evaluated at the X location of the first node, that's 0, okay. Then X evaluated at the X location of the second node, and finally minus the derivative of big X with respect to little x evaluated at the X location of the second node. Okay, and then our shape functions are then X times inverse A. Okay, so there's the shape functions for the first element. Okay, the stiffness matrix is then for the single element the limits of integration here are going to be just the first element, 0 to L over 2. We're going to take the derivative of the ith shape function twice with respect to x, then the derivative of the j shape function again twice with respect to x. So that is the, I guess I erased it, but that's the element stiffness matrix. The formula for the element stiffness matrix when C is equal to 0. So there's no elastic modulus base or anything like that, foundational base. And we need to go from I equals 1 to 4 and j is 1 to 4. So there we have the stiffness matrix, the element stiffness matrix for the first element. Okay. We'll go ahead and find the force vector. So Q is QO 1 minus X over L. All right. And we need to go 1 to 4. Okay. So I've got the output suppressed there, but I'll show it here in just a second. One thing that I didn't do was for the global stiffness matrix, we need to allocate space for it. So if I say constant array 0, 6 by 6, so I just made a 6 by 6 matrix of zeros. Same for the global force vector. Here it's just a vector, so just 6 zeros. Okay. So now that we have the element and the element stiffness and element force vectors, we can put them into place into the global one. So in the global one, we go 1, 2, 3, 4, 1, 2, 3, 4. So there I'm just saying that I want KE to be put in the first 4 rows and 4 columns of the global stiffness matrix. Okay. And same thing, 1, 2, 3, 4, 4 FE. I just want it put in the first. So if we look at what K is now, you see this is in the first 4 rows and columns, but the last 2 rows and the last 2 columns are all 0. Okay, and same thing for F. Okay, the last 2 are 0. Okay, so then we essentially take from here down. So that's the first element's done. It's been assembled. If we put that, everything we did here, except now we're going to go from L over 2 to L. So I'm just changing all of the limits of integration, all of the anywhere I defined a domain. I'm going to redefine it to be L over 2 to L. Okay, and then on the assembly, now we're going to go 3, 4, 5, 6. 3, 4, 5, 6. Okay. So I'm just reevaluating everything. Now, if we look at what K is, oh, 3, 4, 5, 6. Okay, so now we have that for K and that for F. All right. So now we need to apply the boundary conditions. Okay. So the boundary conditions, again, here's the problem. Okay. So at the first node, when you have a fixed support like this, there can be no deflection and no slope. Right? We okay with that? So I could, and I've done in the past, just take those first 2 rows off, drop them, and first 2 columns, and then just operate on this condensed matrix. And we could do that and solve it that way. But as I mentioned in class before, there's another way, in that if we set the first value to 1 and everything else to 0, and the second value to 1 and everything else to 0, and then put 2 zeros in the force vector there, that's the same thing as saying U1 equal to 0, theta 1 equals 0. Okay, so I'm going to do it that way this time, just to do something different. So what I'm going to do here is I'm going to say for the first and second rows of K, I want those to be set equal to an identity matrix that is 2 rows and 6 columns. Right? So that's right there is what I set the first 2 rows of K equal to. So if we look at K now, see how it looks now? Alright, and we can do the same thing. We can say set the first value of F equal to 0 and the second value of F equal to 0. Alright. Now we need to apply, we have an external force and an external moment. Okay. So the external force is applied to the deflection at node 3. So that appears in the 5th element of the force vector. So if I say that the 5th element, we want to add whatever's there because there's some value due to the distributive force. I don't want to change that. So if I add whatever's there, add F0 to it. And the same thing for the 6th where the moment appears. I'm going to add. And if you notice, That's a negative moment if we use the right-hand rule. Okay, so we're going to add minus MO there. So now F looks like this. So whatever was there, we're going to add FO to, and whatever was there, we're going to add MO. So that's what that plus equals does versus just equals. Okay, so now we have everything we need to solve it. So we can just say sol equals linear solve K F. I'm just going to reevaluate everything to make sure it works. And if I just say simplify matrix form. So that is the solution, and it looks correct to me. I know that's correct. So these are the values of the displacement and slope at the nodes. That's U. Well, U vector, which is, it's this. That's what we solved for. This was K. That's it.